Okay, yet another in a long series of problems involving land that needs to be fenced, in this case, in with the minimum cost required, or minimum cost possible. So the situation is you've got this rectangular plot of land, and what's going to happen is a certain type of fencing that goes on two ends will be $3 a foot, and then the opposite ends are going to be the other pair of opposite ends are going to be $2 a foot, and we can use a maximum of $6,000, and we want to get the maximum area that we can get. So, as soon as you hear maximum area, you're thinking, okay, well, that's what we want to maximize. That's what we want to optimize in this problem. But the problem is, again, we have two variables, and we have we haven't worked in that constraint that we can only use $6,000, because we want to make this area as big as possible. Just make X and Y as big as you want, you're going to get a giant area. But we have to watch our cost here. So the cost is going to come into a thing where let's say this is the side that costs $3 per foot. So I'll make a little note of that here. This is the $3 per foot section, and then this side is the $2 per foot section. So we are going to use $3 a foot here and $3 a foot here. So if there were like 30 feet here, that would be 3 times 30 would be 90 feet, $90, and then over here would be another 90 up there. So the amount of money that we're going to use for the fencing for the $3 per foot stuff is going to be two sides that are each X long, and they're going to be $3 a square foot, or $3 a linear foot. Now, there's going to be two Ys, and they're each going to be $2 per foot, and that total has to be $6,000, or certainly no more than $6,000. So if we clean that up, we get 6x plus 4y equals 6,000, and that's essentially our constraint equation. I would absolutely take advantage of the fact that everything's got a common factor of 2, though, and we could reduce that and say 3x plus 2y is equal to 3,000. And we can use that as our constraint equation. So we're going to take this equation that we just came up with and solve it for y, and that way we can use that up in the area equation. So let's say 2y would be 3,000 minus 3x. So y would be, dividing everything by 2, 1,500 minus 3/2 of x. And if we take that expression for y and drop it in up here, we get the area as a function of x, and it's going to be x multiplied by y, which is 1,500 minus 3/2 of x. So cleaning that area function up to get it ready for a derivative, 1,500x minus 3/2 of x squared. This one looks like it's going to be pretty friendly. As far as taking the derivative, we can now take the derivative, set it equal to 0. We're going to get 1,500 minus 3x, set that guy equal to 0, and we get 3x equals 1,500, which means x equals 500. Now, to find out if that represents a maximum area, we could look at what a double prime is, check the second derivative test. A double prime would just be -3, taking the derivative of that guy, which of course is less than 0, which means the function is concave down, and therefore a 0 slope when it's concave down represents a max. So by the second derivative test, we verified that an x value of 500 is going to be your maximum area. And I guess it says find the dimensions, so we should probably go and find what y is. So y is simply 1,500 minus 3/2 of 500, which is 1,500. 500 over 2 is 250, and 3 times 250 is 750, and 1,500 minus 750 is 750. So our plot should be 500 by 750 for maximum area. So a pretty straightforward approach. Again, using the constraint function to come up with a way to express one of the variables in terms of the other, and then straight up derivative, set it equal to 0, and verify that it's a max or a min, whatever the case calls for.